Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to go over how to calculate the equilibrium constant from measured equilibrium concentrations. So let's get into this. So here we have our equation, and so we've been learning how to set up our K expression, but we haven't really put any information in there to calculate. So the simplest way to calculate it, or the simplest situation or circumstance that you're given, is where they give you the equilibrium concentrations right off the bat. So they give you all the equilibrium concentrations. So in that case, all you need to do is just plug them into your K expression. So let's get our K expression for this equation here. So our K expression for the equilibrium constant for this one would be, our product is HI, so it's going to be the concentration of HI, and that's raised to the second power because we have a coefficient 2, and then that's going to be over these two here. So we have the concentration of H2 multiplied by the concentration of I2. And both of these have one coefficient, so we don't need to put the coefficients there. So this is our expression. So in this case, for this example, they gave us the equilibrium concentrations. So all we need to do is take the concentrations, plug them into our equation, and calculate what the answer is. So we plug those in, and we get 0.78 squared over, and then both of these are 0.11. So this is going to be, I don't know why I have that as square brackets. So that would be like that. And so we have 0.11 multiplied by 0.11 for both of those. And then all we do is we stick that into our calculator, we plug and chug, and the answer becomes 5.0 times 10 to the 1, or 50. Okay, so notice that I didn't put any of the units in there. I didn't put concentration in there because, again, when we're doing concentration, as long as we're doing molarity, then we're comparing that to the reference of 1 molar. So it's 0.778 molar over 1 molar. The units cancel out. So there are no units for your value. So this would be just a unitless number that we get. And so that would be the expression for this, would be the constant for this reaction, the equilibrium constant for this reaction at a certain temperature. Okay, so one of the things I want to point out right now is you got to remember that the values that you put in here, the concentrations, the equilibrium concentrations that you have for this reaction or any reaction, is going to depend upon the initial concentrations you start with. So these equilibrium concentrations will be different if you start with different concentrations initially. But that's not going to change the constant at equilibrium. So the equilibrium constant will always be the same, no matter what the equilibrium concentrations are, and no matter what initial concentrations you start with. So here I have a little table here. So here's the concentrations that we start with initially. So if I start with 0.5 molar H2 and 0.5 molar I2, and I don't have any HI to begin with, so I have zero product to begin with, at equilibrium, I end up with the 0.11 and 0.11 for both hydrogen and iodine, and I end up with the 0.78 for HI. But what if I start with different initial conditions? So if I start initially with 0, 0, 0 H2 and 0 I2, and I just start with 0.5 molar of the HI, then at equilibrium, what I end up with is 0.055 of the molar of the H2 and then 0.055 molar of the I2, and I end up with 0.39 molar of the HI. But if I take these numbers and plug them into the equation like I did before, I will end up with the same value here. I end up with 50. Same thing here. So if I start with 0.5 molar of my H2 and 0.5 molar of the I2, and then 0.5 molar of HI, and I let the reaction go at equilibrium, I end up with different concentrations. Here I end up with 0.165, 0.165, and 1.17 molar respectively. But again, if I take these values, these equilibrium concentrations, and plug them into my expression here, I get the exact same constant. So no matter what the initial conditions are, you'll get different equilibrium concentrations, but the expression will still give you the same constant, given that we don't change the temperature. Okay, so what if instead of just giving you all of the equilibrium concentrations and you just plug and chug, what if they don't give you all the equilibrium concentrations? So in order to solve this problem and find the K expression, all you need is one, you need the initial concentrations of your reactants, right? So you need that, and you need you need at least one equilibrium concentration of either a reactant or a product. So as long as you have those two things, you should be able to solve the problem. And the way you solve the problem is using what is called an ICE table. And here is my ICE table. So my ICE table here, I stands for initial concentrations. C stands for the change in the concentration, and E stands for the equilibrium, the concentration at equilibrium. So if you know your initial concentrations of your reactants and you know at least one equilibrium concentration, then you should be able to figure out the rest. And so I'm going to go over this as an example. So here I have my expression. I have my generic equation here. So I have A in the gaseous phase in equilibrium with 2B. So 1A molecule or 1A substance will give rise to 2Bs. And this goes back and forth. So let's assume that I'm given the initial concentration of A for 1.00 molar, and the initial concentration of B is 0.00 molar. But I know at equilibrium, my concentration of A is 0.75. So let's fill in the table. We're going to use our ICE table and fill in the information. So I know that the initial concentration of A is 1.00 molar. So I'm going to put 1.00 for my A. The initial concentration of my B is 0.00, so that's going to be 0.00. And I know that the equilibrium concentration of A is 0.75. So I'm going to put that here under equilibrium. So 0.75. So now I can fill in the rest of the table. So what is the change? Well, I went from 1 to 0.75. That means I lost 0.25. So the way I'm going to do this, I'm going to just put a negative. I lost negative 0.25. So that's the change in the concentration of A. So A went from 1 to 0.25. That's a change of a loss of 0.25 molar. So with that, if I know that I lost some of my A, that means that this A became B. So this is where the balanced equation is really important. So I know that for every A I lose, I gain 2B. So here I lost 0.25. So since B is doubled in comparison to the loss of A, then I need to double the amount. So I'm producing product. So in this case, I'm losing reactant, so the reactant is becoming product. So I'm gaining product. Well, how much? Well, it's by the same amount. So it's going to be a positive 0.25. But because I have the 2 here, I got to double it. So whatever the coefficient is, I put the coefficient here as well. So now the amount of product, or the change in product, is going to be twice as much as the change in the reactant. And it's positive because I'm gaining product, I'm not losing product. And so in this case, what I do is I multiply whatever the change is. It's the change from the initial to the equilibrium. So since I'm starting with 0, that means I'm adding twice of this. So 2 times 0.25 is 0.5. So that becomes 0.50. And so I went from 0 to 0.25. So I went from 0 to 0.5, and I gained 0.5. So this is my equilibrium concentration. And so now that I have both equilibrium concentrations, I can now plug them into my equation. So my K expression for this is going to be the concentration of B raised to the second power over the concentration of A raised to the 1 power. And now I can plug in my equilibrium concentrations. So then I plug those in. So B is 0.5, 0.5 squared, and A is 0.75. So I'm going to put 0.75. And then all I do is I calculate that out, and I get my answer. And let's get the answer here. Get my calculator out. So I calculate this as 0.5 squared, and then I divide that by 0.75 equals, and my answer is 0.33 for my equilibrium constant for this reaction. So that's how you can figure out the equilibrium constant if you're not given all of the information for the equilibrium concentrations. If you're not given the equilibrium concentrations for everything straight off the bat, then if you are given at least the concentrations, the reactions or the reactants, and at least one equilibrium concentration for either the reactant or product, you can use your ICE table to figure out the rest. And then once you've got your equilibrium concentrations that you need, then you just plug those into your expression, and you've got your equilibrium constant. I hope this is helpful. I hope you learned a lot. If you liked my video, please hit that like button, subscribe to my channel. Please hit that notification bell so you can be notified by other videos that I put out. Put a comment in the comment section. Let me know what you think and if you have any questions. Thanks for joining me. Have a great day.